Okay, so hello everyone. I'm very honored today to be here. My name is Abir Messaoudi. I am a PhD student in spoken language processing, and I am presenting our paper entitled Tunisia toward a Tunisian speech emotion recognition system. So I will start with Darwin's studies saying that expression are universal. In fact, we experience 7 principal emotions, which are happiness, sadness, anger, fear, surprise, disgust, and contempt. And we used the same facial expression in order to express them. Even though this is true, it seems that emotions can differ across cultures through our use of language. Languages differ in the words they have for emotions, not only in terms of the number of words for each emotion, but in intonation and in the extent to which a word gives nuances, combines emotions, or tell us what caused the emotion. Having a different word or expression for an emotion state may influence the whole emotional experience. Speech emotion recognition, or SER, is the process of extracting emotional information from speech. It's filled with a growing interest and potential applications in human-computer interaction, in content management, in social interaction, and as an add-on module in speech recognition and speech-to-text systems. And under the assumption that it is a language-oriented task, our goal is to build the first Tunisian dialect speech emotion datasets and speech emotion model. So, as you know, text-independent SER relies on the specific attributes of speech audio signals. In such an elusive task, a data-driven approach is followed. This means that models are trained on data. As a consequence, the performances of STR models is linked to the quality and the organization of the provided dataset, let's say. So about data, speech data sets and use it for building SER systems are divided into 3 types. The first is simulated, which are created by reading the same text by different trained speakers with different emotions. The number of distinct emotions are important. As they have synthesized emotions, they are disposed to have overfitted models around emotions that are different than what is happening in real life and our day-to-day conversation. The second type is the semi-natural datasets, which are datasets that are quite similar to the natural utterances of speech, even if they are made based on scenarios with a contextual setting. The emotion are artificial because speakers here know that they are recorded. And unfortunately, those datasets have a limited number of emotions due to the limited cases of the scenarios compared to other types of datasets like the natural one. So the third and the final type is the natural datasets, which are made of fully natural emotions, which eliminate the problem of being artificially made. They are very effective because they perfectly represent our daily life due to the existence of the background noise, for example, or multiple emotions, and also of the dynamic variation of the speech. But however, those characteristics make the detection and the modeling of the emotions here more complicated. So in order to build our first Tunisian speech emotion recognition datasets, we focused on Tunisian series and TV programs publicly available on the internet. we saw suitable and useful audios that are rich in emotion. We focused on the quality and diversity of the sources. For example, audios have to be quite clear and contain both males and females of different ages, situation, and context. We selected also different audios for actors playing their roles in a sequence, and we manually extract the ones that contains explicit emotion states. So in conclusion, our dataset is considered as a semi-natural dataset. Once audio sequences containing emotions are collected, we convert them to be in the required format. And to take out the best emotional scenes from the audio, we choose to apply a segmentation process, which separates the input audio sequences into small utterances with an average of around 1 second with clear expressions, which mean the whole word or sentence that contains a significant emotional state without ignoring parts of the words and without overlap between the speakers. For the validation guideline, we only kept audio based on the following criteria. Each utterance should contain only one subject talking and having only one scene. Sound should be clear without noise so that you can hear the speaker clearly talking, and utterances should not contain music, should not contain silence, or be of a bad quality, of course. So for the annotation process, the annotation process is then divided among 3 Tunisian native speakers. All are at their high-level education, and we choose to keep only the 4 primary emotions, which are happy, sad, angry, and neutral. And we also mark the gender of the speaker in a segment, which means he is male or female for long-term purpose. Here you can find a typical architecture of a speech emotion recognition system. Raw audio in a speech emotional datasets are first fed to a feature extractor component to extract the relevant information. We find multiple, in fact, technique of feature extractions in the state of the art, from the prosodic features like pitch and energy to a spectral like MFCCs and MER spectrogram to then deep features. The selected features from raw audio are then passed to a classification model to predict the emotion at the end. A classification model could be a simple machine learning neural network or a pre-trained model. In this work, we actually experimented 2 pre-trained models. The first one is Google VGGH. The Google VGGH is a variant of the VGG model, and they have very similar architectures. It was pre-trained on the audio state database, which is a collection of more than 2 million human labeled audio clips collected from YouTube videos with 10-second length each. This database contains over 600 sound classes, including music, speech, vehicle, etc. So the VGGH model architecture is constructed of 4 blocks: 2 convolution and max pooling layer, 2 fully connected, and finally fully connected layer that gives the embedding vectors. VGGH model gives a high-level embedding from audio input features, and those embedding could be fed to a downstream classification model as input. Our second chosen model is the well-known pre-trained Wave2Vec 2.0, which is a framework of self-supervised learning of representations from just raw audio. It has obviously two stages. The first stage is the pre-training stage. It enables learning powerful representation from speech audio alone. And second, the fine-tuning stage for downstream tasks like ASR and so on. So to train our Tunisian model, we used fine-tuned Wave2Vec models on the automatic speech recognition downstream task to better determine the context representation for the input audios. We then built a neural network as a classifier on top of it to predict the class of each audio. In fact, we fine-tuned the multilingual Wave2Vec XLSR for the automatic speech recognition downstream task in two languages or in two dialects. First, on the modern standard Arabic using the Mozilla Common Voice dataset, which consists of 10 hours. We choose only a subset of 10 hours. And then on the Tunisian dialect using the stack datasets, and we choose only 4 available data hours which are available. So the results of fine-tuning Wave2Vec on the ASR downstream task are below in the table. And finally, we built a classification layer on top of the two fine-tuned models to perform the emotion classification. For both models, we adjust the number of epochs and the value of the learning rate to find the best results. And we obviously split our balanced data into 80% as training and 20% as a validation set. As a result of our experiments for the first approach, consisting of a neural network classifier on top of pre-trained CNN that outperformed the current state-of-the-art emotion classification model on EMOCAP audio-only datasets by a relative accuracy of 6.3%. And by training it on our constructed Tunisian dataset, we achieved 60% as accuracy. This proves the applicability of transfer learning for the speech emotion recognition task. For the second approach, fine-tuning the multilingual Wave2Vec 2.0 XLSR model with modern standard Arabic and Tunisian dialect ASR, and then training them on speech emotion recognition gives good results, actually. However, we notice that the Wave2Vec, which is pre-trained on Tunisian dialect ASR, outperforms the MSA1. In fact, fine-tuning Wave2Vec on a dataset in the Tunisian dialect enhanced the results by 8%, which is our best result until now. Finally, to wrap up our work, in this work, we described our methodology to build a Tunisian speech emotion recognition dataset. We detailed the process of using two large pre-trained models, the VGGH and the multilingual Wave2Vec 2.0 XLSR as feature extractors for the speech emotion recognition task. Our work is a first step, honestly, for the speech emotion recognition task on the Tunisian dialect, since our satisfactory results could be improved in future work by augmenting the dataset's size, or by including more sentiments, or also by applying enhancement technique like noise removal and speech enhancement. Thank you for your attention.